So a lot of students have a really challenging time wrapping their heads around, well, how did we go from the Rutherfordian model, where we have this positively charged nucleus with some um, electron cloud around it, to the SPDF quantum mechanical model? Like, how did that come about? Well, a lot of it really came in the early 1900s that basically physicists were studying light absorption and emissions, and they found relationships to the wavelengths, to the frequencies and energies, and the way that these electron models were being observed. So it's actually a collection of ideas from a lot of very big names in science, and we will definitely get to that. All right, so first let's go over what some properties of light are. Okay, light is um, excited electrons, and they are particles, because they're electrons, that travel in waves. So really what we see here is not this whole line, but you actually see like this dotted line approach. Okay, so this dotted line is going to represent these particles moving in a wave-like behavior. All right, so when it comes to our different particles, um, there's a couple of things that we need to point out. Is that there is this center line right here, which is going to be your origin. Okay, and this origin is what everything fluctuates around. Okay, the top of a wave is called the crest, the bottom of the wave is called a trough, the height or the depth of a wave is called the amplitude, and that is the distance between the trough and the amplitude, or the crest and the amplitude. And then the wavelength is exactly what it sounds like. It is the length of one full cycle of a wave. One complete up and one complete down. One complete crest, one complete trough. So you can measure it from crest to crest, from trough to trough, some arbitrary point to arbitrary point. It doesn't really matter, just as long as you have one complete cycle. Okay, so for notes purposes, we have our origin in our center line right here, our wavelength, which is the Greek letter lambda. Um, it kind of looks like an upside down Y. It kind of looks like a wave, I think. Um, so this is that distance here from your crest to your crest. And then you have your amplitude, which is going to be the height of the wave. And if you know anything with music, when you turn up the amps, what are you turning up? You were turning up the volume. Okay, so that's basically what you're doing. When you turn up your amps, you are basically making your sound wave louder. So a lot of this stuff obviously applies to sound as well as light. And then the last major concept that we're going to spend some time on is frequency. All right, frequency is how often we see a wave go by. Some textbooks and some scientists use F, but most likely you will end up seeing this new letter, which is your Greek letter NU, not NEW. And it kind of looks like a cursive N or V. And that basically says the number of waves that you have per second. So per second means 1 over s, which is as the same as s to the negative first, or inverse seconds. This unit tends to give some people some trouble. Some scientists don't like it either. So the equivalent unit would be the hertz, okay, HZ for short. And these things all mean the exact same thing. And it's basically figuring out your number of waves per second. So when you say how frequently something is going on, you are asking how often they go on. How frequently do you brush your teeth? 2 times a day? Do you have braces? Do you brush them 3 times a day? Sometimes if you're late night snacking, 4 times a day if you get stuff stuck in your teeth. I have bad teeth, so I tend to brush quite often. All right, so when it comes to all of your Waves. There is a certain spectrum, a list of our different types of radiation, electromagnetic radiation, that exhibit this same wave-like behavior as it travels through our universe. Examples include X-rays and ultraviolet, infrared light, microwaves, radio waves, etc., etc. And there's obviously much more than that. So you might have seen something very similar to this in the past, and that is going to be exactly how the wavelength is going to relate to our frequency. All right, so up here you'll see the wavelength, here you will see the frequency. So the longest waves are going to be here, and these are going to be the shortest waves. All right, so the longest waves are going to have the lowest frequency, and the highest frequency is going to have the shortest waves. So frequencies that are like 10 to the 6th to 10 to the 10th, these are going to be your radio waves, which bounce off of mountains and buildings and all that kind of stuff. And those aren't really going to hurt anybody. They don't really do anything too dangerous because they are such big wavelengths. They have very low energy, um, and you don't really see a lot of them at one time. Okay, a microwave is going to be in our 10 to the negative first to 10 to the negative third. I misspoke before. The radio waves are 10 to the third to 10 to the negative first. So this is about 1,000 to a tenth of a meter, and roughly the size of an ant. That's what we're looking at with our microwaves. They are going to excite water particles and water molecules. So you'll be able to see them move around and do things like in a microwave. Infrared light, which is what we use in our remote controls and infrared goggles, are 10 to the negative third to 10 to the negative sixth. That's like the size of the eye of the needle to what we see in pond water, the protozoa. If you shine a remote at something, it's not going to hurt anything with that infrared light. But that's where you start to get into very, very small substances like our visible range. Okay, so this is the human visible range. We can see between 10 to the negative 6th and 10 to the negative 7th. So we can see somewhere between 400 and 700 nanometers. You'll see that the red spectra is going to be here closest towards the infrared, and the violet spectra is going to be closest towards the ultraviolet. But this is how it's all related. So all of these different wavelengths, which instead of using numbers like 10 to the negative 7th, we end up using nanometers. So we see from 400 to 700 nanometers. This is why that chapter with all the metric prefixes was so important. Next, we have our ultraviolet light, UV light from the sun. That is 10 to the negative 7th to 10 to the negative 8th in size. That's the sizes of viruses and proteins. This we cannot see. Okay, we cannot see here. We cannot see here. We can only see this very, very small, narrow window between here and here. But the ultraviolet light, this is where these wavelengths are going to be so small in space that they can do damage. Okay, and the damage can be sunburn and cancer and things like that. X-rays are even smaller than this, 10 to the negative 8th, 10 to the negative 11th. These go through soft tissue, and that's what is stopped by, and we saw our whole atomic nuclear chapter before this. This is where they are stopped by bone, and why, you can see x-rays for teeth and see the itty bitty cracks in our fractures and stuff like that. And then lastly, we have our gamma rays, and gamma rays are going to be so super small. They're going to do a lot of damage. These are what actually test the structural integrity of buildings after earthquakes. And they're going to be the absolute smallest ones. Okay, so these gamma rays will do a lot of damage. Radio waves, on the other hand, will not. But you'll see that there's a sliding spectrum. The more often you see a wave go by, the higher the frequency. The less often you see a wave go by, the lower the frequency. And one of the things that I always like to point out here is imagine you were on a little itty bitty boat, okay, and you were here in this part. Okay, this right here, the boat, you're going to see very calm seas. But if you were on a boat here, oy, 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 this would be dangerous. All right, so that kind of helps.